Corrosion Part 3. Hello everyone, this is Corrosion Audio Lecture 3, Further Thermodynamics for Electrochemical Corrosion. So, I hope everyone is enthusiastic for more thermodynamics. There is an important reason for the more thermodynamics we're looking at today, because the two subjects of this lecture are, first of all, the Nernst Equation, for calculating electrode equilibrium potentials when we have non-unit activity. That means with dissolved ion concentrations which might be different from 1 mole per decimeter cubed, or 1 molar. Secondly, we are going to look at the construction of pH-potential diagrams, or Pourbaix diagrams, which will be used to look up whether a metal will be immune from corrosion in some measured situation, or more likely, will the metal corrode actively dissolve, or will it be passive against corrosion? And those two questions, we cannot yet answer them with just the first lecture of thermodynamics, so we have some more from today. Before we look at more thermodynamics algebra, I want to reflect on this title slide with some excellent Japanese-style art that a gentleman on YouTube, links in the caption below, has etched onto titanium plates using a controlled electrochemical corrosion process. The reason for looking at these nice titanium plates is, as I said in Lecture 1, metals like aluminium or stainless steel are often passive against corrosion, because they grow a thin oxide surface, about 1 to 10 nanometers thick, which is solid and impermeable to water. And because the oxide is the thermodynamically stable phase of those alloys or metals, the further corrosion pretty much stops once the surface oxidizes a bit. And if corrosion occurs but produces an impermeable solid oxide and then corrosion essentially stops, then the metal is called passive. Because I told you the passive layer is just 1 to 10 nanometers thick and too thin to see with the eye, you might, if you were empirically minded, you might have some lingering doubts as to whether I was making up this entire story about the passive layer. These nice titanium art pictures show you that I was indeed telling the truth. And the reason it tells you this is because you see around the edge, this is normal titanium, which is just silvery, you expect it to be, because the passive oxide is too thin to see. If you watch the YouTube clip though, the artist has used a high voltage etching pen to artificially electrochemically corrode the material to make the passive oxide thicker, and the different colours which are sketched onto the titanium are actually Bragg reflection colours, or thickness colours, in which the thicker the film becomes, the longer the wavelength of the main part of the reflected light. And in that case, because the thickness of the oxide gives you a colour, you can see the passive oxide film on these titanium things. So the coloured bits of it are, in this case, a few hundred nanometers thick, and so that proves to you that the passive layer really is there. And they look nice, as well as being a nice electrochemical corrosion demonstration. They also happen to be in one of my favourite line art styles, similar to the Japanese landscape prints at the bottom of the slide by the legendary artist Hiroshiga. Okay, Lecture 2 covered electrochemical corrosion notation, and we concluded that corrosion happens if the metal we are worrying about acts as the anode of an electrochemical cell. Then we found an equation for predicting if the metal works as an anode. And so far, we derived this equation for the case of unit activity, meaning standard concentrations like 1 molar. The equation said the electrochemical process happens if the cell potential, given by the standard electrode potential of the cathode minus the standard electrode potential of the anode, is positive. So that was important because we could then look up the standard electrode potential of the metal, and we could see if it forms an anode in combination with a mixture of oxidizing agents in the environment, for which we measure the potential of the cathode, essentially with a voltmeter. So this made it simple to predict if corrosion would happen under standard conditions. What we need to do now is expand this prediction for non-standard concentrations, such as when some piece of metal is dissolving into a dilute solution of ions, like is the case when a steel boat or an oil rig corrodes in seawater, for example. So this is a very important question, because let's look at page 16, section 2.10 to see why. In this example, I want to predict if copper dissolves into seawater. In reality, I could find out from experimental observation that copper does dissolve in seawater. Slowly, but it does dissolve. But the problem is, using the equations we have so far, in the data for this example, the standard electrode potential of the copper in equation 240 is plus 0.337 volts SHE. Remember from last time, this is equivalent to saying if we built a copper dissolution cell with the process shown in equation 2.41, where copper is at the anode, and at the cathode we have pH 0 strong acid, actually. If we set up that, we can see that the potential of the cell potential would be negative. It would be the potential of the cathode minus the potential of the anode, and that would come out as minus 0.337 volts. And our criterion for a cell process to take place is that the cell potential is positive. So in this example, in equation 2.41, it is implied that the copper would not dissolve into even into strong acid at pH 0. So it would seem even less likely that copper metal would dissolve into seawater, which has a mildly alkaline pH of about 8. We need to know, therefore, how do we improve our theory so that it doesn't make this experimentally incorrect prediction of copper not dissolving into, for example, seawater. To make this improvement, we need the Nernst equation to deal with non-standard concentrations of ions. So, section 2.10.2 says the improvement we need to take into account is done like this. So it shows we're considering here copper dissolution in equation 2.43, and we're looking for the Gibbs energy change of this process, which is the standard Gibbs energy change, plus a term to correct for the possibly non-standard ion concentrations. So this equation, as I said, is taken as a starting point in this course. Atkins Physical Chemistry, Chapter 9, in the 5th edition, if you want to look up a recap of where this Gibbs energy change equation comes from. Now, imagine we have this copper dissolving into some solution. We're asking, does the copper dissolve into a solution where we have extremely dilute copper ions? And I'm considering what happens if we have 1 picomolar, or 10 to the minus 12 moles per decimeter cubed of dissolved copper 2+ ions. Assume for the moment that the pH, keep things simple, the pH is 0, so we do have unit activity of protons or hydrogen ions. In that case, we can plug these concentrations into equation 2.43 using the reaction quotient, this term to do with concentrations in equation 2.44. And in that case, we would find out that the reaction has just about a negative Gibbs energy change, so we would predict that the copper would dissolve if the solution contained extremely dilute copper ions. And this makes up half the reason why copper dissolves in seawater. It's because copper ions in seawater are dilute. The other half of the reason why copper dissolves in seawater is that the reaction isn't actually copper metal dissolving to give copper 2+. It actually forms a chloride complex. and the chloride complex is more stable than copper 2+ ions, so the reaction actually has a more negative delta Gibbs energy change than is implied by equation 2.43. And taken together, the fact that we have dilute copper ions in solution, and those ions are actually more stable copper chloride complex ions, it turns out copper does dissolve to more than 1 picomolar concentration in seawater, even though it's at pH 8 in actual seawater. Equation 2.46 tells us the reversible cell potential for an electrochemical process with one anode and one cathode at possibly non-standard concentrations, and this is called the Nernst equation for a complete cell. So this thing, equation 2.46, is everything we need to handle the simple example question about copper dissolving, as in section 2.10.2. If the cell potential from equation 2.46 turns out to be positive, then the copper at the anode is expected to dissolve. But remember, in general, we want to solve harder problems. Harder problems come up most of the time in engineering practice because we usually only know the exact details about the metal that we're interested in, because we bought it and installed it. But still, we want to know if this metal corrodes or is an anode in some complicated environment, which might have more than one oxidizing agent, more than one possible cathode, and there might also be unknown concentrations of the oxidizing agents, not just as simple as 1 molar hydrogen ions, which we had in the example above. So we need to be able to handle this harder case in some way, like making a measurement to estimate the cathode potential exerted by the mixture of different oxidizing agents. But there is no way to do that using simply equation 2.46 or its general form 2.47, because those equations for one complete cell contain a single combined term which describes a system with one anode and one single cathode. Instead of that, we need to do some more work to separate out the anode and cathode terms there so that we can replace the cathode term with a measurement. Algebraically, that's easy enough to do. We just take the general equation 2.47 and we break it apart into equation 2.49. We do that by separating the anode and cathode elements in the log term of 2.47. Then once we've done that, we expand equation 2.49 into equation 2.50 by remembering equation 2.33, which said that our standard reversible cell potential was equal to the standard electrode potential of the cathode minus the standard electrode potential of the anode. At this point, then we inspect equation 2.50, and we see we can simplify it into equation 2.53 by grouping together the cathode terms and the anode terms. The cathode terms give us one cathode equilibrium potential term as shown in equation 2.51, and the anode terms likewise group into one anode equilibrium potential term as in equation 2.52. Then we have this very simple equation 2.53, which allows us to evaluate whether corrosion happens at any ion concentration in a dissolved in solution. Equation 53 just says we compute the cathode equilibrium potential of the oxidizing agent minus the anode equilibrium potential of the metal, and this gives us the reversible cell potential for the system. If the reversible cell potential evaluated by equation 2.53 is positive, then the corrosion process with the metal at the anode is predicted to happen. Each of the electrode equilibrium potentials on their own are given by the Nernst equation for a single electrode. In general, that is equation 2.54 or 2.55, which are the general cases for any electrode process for which 2.51 and 2.52 in our derivation were a specific example. Remember, of course, we often only need to evaluate equation 2.55 in the general case for the possible metal anode, because the cathode equilibrium potential is going to be replaced by one measurement of a real environment containing multiple possible cathodes. So that on page 17 up to equation 2.55 is the main part of the Nernst equation derivation dealt with. A couple more things to say. First of all, the Nernst equation is often written with logarithm base 10, as in equation 2.56. The reason for that is because in corrosion we often think about concentrations of chemicals in terms of powers of 10. So we think about 1 micromolar or 10 micromolar dissolved copper ions. Or we say going from pH 3 to pH 2 is a 10 times increase in hydrogen ion concentration. So because chemists often work in base 10, the Nernst equation we often write using a logarithm to the base 10. So equation 2.56 is the form of the Nernst equation for a single electrode that I would recommend you learn. If you are more comfortable with having the log term be negative, but with the arguments of the log term the other way up, that's also okay. In corrosion, it's often written that the electrode equilibrium potential is the standard equilibrium potential plus some terms where the terms include the logarithm of oxidized species over reduced species, but you can also have minus the term with log of reduced species over oxidized species. So it's whichever you're more comfortable learning to use. Page 18, section 2.11 is an example of using the Nernst equation to calculate the reversible cell potential difference of something called a concentration cell. The example question is this. It says, an electrochemical cell consists of a silver anode, silver metal foil anode, dissolving into an aqueous solution which contains dilute silver ions at 10 millimolar concentration. And the cathode of this process is it's connected by a salt bridge to silver ions at a higher concentration of 100 millimolar, which are said to be electroplating onto another piece of silver. We're told the temperature is 298 kelvins, which we do need to know, because the question is calculate the reversible cell potential difference using the Nernst equation. So how do we do that? So we say that the cell notation is given under the solution, and if we have this cell notation, that's algebraically how we have this picture of the dissolving silver foil in dilute solution, and the other electrode, the cathode, where silver ions are plating out from concentrated solution. All we need to do is use the Nernst equation to get the equilibrium potential for the anode and separately for the cathode, and then use equation 2.53 to identify that the cathode equilibrium potential minus the anode equilibrium potential gives the reversible cell potential. If we plug in the given values, then the reversible cell potential comes out to be plus 59 millivolts. So the plus value, the positive value, means this process is predicted to go forwards spontaneously. And since the change in state of the forward process is equivalent to silver ions migrating from a high concentration to a low concentration, it's right that we expect this, we predict that this will go forward spontaneously. Section 2.11.1, this is the analogy between redox potential and temperature. Now, this section is not talking about a perfect analogy, but this is a helpful picture to get a concept as a starting point for what the redox potential exerted by an environment on some poor unsuspecting metal means. So the picture here shows a saucepan of boiling oil, ready for some delicious deep fat frying. From your knowledge of deep fat frying, you should be able to answer some questions. And the bonus question is, why is this situation a somewhat helpful analogy for describing the oxidation potential exerted by a corrosive environment? Question 1 what is the temperature of the oil in the fryer? Answer, probably about 220 to 250 Celsius is the boiling point of a typical frying oil. Question 2. What would happen if some water, a few milliliters of water, were added to the fryer? Answer, do not do this because it is notoriously dangerous, but a small amount of added water would boil in a burst of steam, which would give off dangerous splashes of oil as well. The reason the water would boil is because it would quickly take in heat from the oily environment, which is far above the water's boiling point. Question 3. How would the temperature of the boiling oil change if the pressure was different? For example, if the deep fat fryer was in a lower atmospheric pressure in a cafe situated near the top of a mountain. Answer, the boiling point of the oil would then be a bit cooler. So I think the temperature of the oil is a somewhat helpful analogy for the oxidation potential which a chemical environment exerts on a bit of metal. First, the water in the pan of hot oil, it would be transformed into a different state by gaining energy in heat transfer. This resembles the way that a piece of metal like zinc dropped into an oxidizing environment might be transformed by losing electrons to the more oxidizing environment. So they're both transformations going on by transfer of something, energy or electrons. Second, the corrosion of the metal talks about an anode process driven by a difference in redox potential. It is predicted to happen, the corrosion, if the cathode potential of the environment is greater than is more positive than the equilibrium potential of the metal. And this is loosely analogous to the way that heat transfer in the deep fat fryer would be driven by a difference between the boiling points of the oil, the environment, and the small amount of added water. Third, the way the boiling point of the oil increases with increasing ambient pressure somewhat resembles the way that an oxidizing agent like nitric acid exerts a higher oxidation potential the more concentrated the acid becomes. That's what we learn from something like the Nernst Equation. None of this is a perfect analogy, but it gives a visual picture of a starting point to think about how an oxidizing environment affects a metal. Think of an oxidizing environment as being destructively transformative to metal by electron transfer in a somewhat similar way that hot boiling oil would be destructively transformative to liquid water because of heat transfer. In this analogy, a metal which happens to be immune from corrosion, such as gold in pure nitric acid, this happens because the equilibrium potential for the gold's dissolution is more positive than the oxidizing potential exerted by the environment. And so the oxidizing potential of the environment is the cathode potential of the oxidizing agent in this case. So the immunity to corrosion of gold is analogous in this example to the way that, for example, something with a high boiling point might not boil if it was put into the deep fat fryer. So, for example, some kind of silicone oil might not boil if it was put into the deep fat, because the boiling point of the silicone oil to vaporize might happen to be greater than the boiling fat's temperature. Okay, good. Page 19, section 2.12, gives some sample data for predicting whether corrosion happens using the one thermodynamic data value for the metal and one measurement of the environment. So from equation 2.53 and the idea behind equation 2.26, we get this equation 2.57 saying if the reversible cell potential difference is positive with a metal anode, we predict the metal corrodes. So the reversible cell potential difference is the cathode equilibrium potential minus the anode equilibrium potential. The equilibrium potential for the possible metal anode is easy to deal with. We calculate it by finding the relevant standard equilibrium potential in the first table, table 2.1. And for example, we might have steel or say iron metal dissolving to Fe2+ ions, and it has a standard equilibrium potential of minus 0.44 volts SHE. We take that and we correct this for the actual dissolved ferrous ion concentration in the environment using the Nernst equation, equation 2.56. So that gets us the anode equilibrium potential term. So the equilibrium potential for the cathode is something that's a bit harder to get. We measure it indirectly. What we actually directly measure is something called the galvanic potential, or the mixed surface potential of the metal as it rests in its environment. And the galvanic potential does depend on what the environment is. So in table 2.2, some examples are given here for a specific environment. This is metal in pH neutral, fairly pure water, or in other words, in fresh groundwater in neutral soils, for example. There are many possible table 2.2s for different environments, whereas the standard equilibrium potential table 2.1, there's just one of those tables. So, although there are many possible table 2.2s, it's very easy to measure the galvanic potential which we need in a particular case, which is done as shown in the picture on the next slide. In this picture, we say a real metal in a real environment has several simultaneous electrochemical reactions happening on its surface. But because the metal is a good conductor, that's not a problem, because there is just one uniform electrical potential all over the metal surface, and we can easily measure it. It's called the mixed surface potential if it comes about from a mixture of several different electrochemical processes, and measuring it is as easy as shown in the top right of the slide. We have essentially a voltmeter measuring between a reference electrode. Conceptually, it's easiest if it's a standard hydrogen reference electrode, up to the potential of whatever the metal surface is as it sits in its environment, and of course there's ion contact, so both the reference electrode and the metal we're measuring have to sit in, for example, the groundwater. So we can easily measure a galvanic potential that way, and we're also going to call it a mixed surface potential. The mixed potential, it's some sort of average. It's the potential of electrons on the metal surface, and it sits somewhere in a pseudo-steady state in between the equilibrium potentials for the cathode reactions, which are higher, and the equilibrium potential for the anode reactions, which are lower. So when we want to predict corrosion, all we actually need to do in practice is ask if the mixed surface potential is more positive than the equilibrium potential for the possible metal anode. If yes, the mixed surface potential is more positive than the equilibrium potential of the possible metal anode, then that metal will be corroding. The justification for that is that we have this inequality where the mixed surface potential is some value between the anode and cathode equilibria. So, if the mixed surface potential is more positive than the metal equilibrium potential, then definitely there will be cathode equilibrium potentials much more positive, or at least more positive than the metal equilibrium potential, which means that in equation 2.57 there will be some positive reversible cell potential for an electrochemical process with the metal at the anode and one of the existing cathodes at the cathode, and therefore the metal will corrode. Conversely, if the mixed surface potential is lower than the metal equilibrium potential, then the only electrochemical processes which have a positive reversible cell potential and will proceed involve the metal being at the cathode. So in that case, if the mixed surface potential is lower than the metal equilibrium potential, corrosion is predicted to not happen. Okay. On the bottom of page 20, there are a couple more comments about the mixed surface potential. Now, this mixed surface potential is always somewhere between the equilibrium potential or potentials of the anode or anodes, and those are at a lower potential than the mixed surface potential, and the cathode or cathodes have a higher equilibrium potential. But the exact value of the mixed surface potential is difficult to specify just from that information because it has some sort of weighted average value between the equilibrium potentials of all the processes on the metal surface. But fast or strong electrochemical reactions have a large weight in deciding this average, and slow processes or processes involving species at low concentration have a low weight. So if we look at zinc in table 2.2, it has a galvanic potential close to the standard equilibrium potential for zinc. And this comes about because the zinc dissolution is a fairly significant process on zinc metal, and other reactions like hydrogen ion discharge are not very strong. So the galvanic potential for zinc is close to the standard equilibrium potential for the zinc. In comparison, on iron, and even more so on rusted iron, the mixed potential is quite a bit more positive than the metal dissolution equilibrium potential. So that comes about with iron and steel because iron is a pretty good catalyst for the reaction of oxygen in the environment, and rust is actually an even better catalyst than shiny steel. So the mixed surface potential on iron, or rusty iron, is weighted to a higher value than the standard equilibrium potential of the iron. So this is also, we'll be able to understand when we look at kinetics, this is also why rust is a very bad problem and is described as autocatalytic. It's why once a bit of rust appears, it provides a really good catalyst for the promotion of further corrosion. And so it's often important to clean away rust when it appears. We'll come back to that in the future during the chapter on corrosion protection. Page 21, section 2.14, talks about corrosion and pH. pH is extremely important for deciding if corrosion happens and how fast it happens. The second point, that pH can decide how fast corrosion happens, is the easier one to explain, so let's deal with that one quickly. The explanation is that quite often electrochemical corrosion speed is rate limited by how easily ions in solution can migrate between the anode and the cathode and keep those processes in balance. Now, pH strongly affects the ion conductivity of solutions, so in the case of neutral pH 7 solutions like fairly pure water, often those might be an environment where corrosion is quite slow because the overall process is rate limited by slow ion transport. Conversely, strong acids and strong alkalis can have high ion conductivities, and those are environments in which there might well be no rate limiting from ion conductivity, and there can be quite fast corrosion. But let's then come back to this first point. Does the corrosion happen at all, say in this strong acid? So the question about how pH controls whether corrosion happens at all, in other words, is there active corrosion, passive corrosion, or no corrosion because the metal is thermodynamically stable, so that is the contribution of pH is explained by the Nernst equation as shown in equation 2.58. In 2.58 we're talking about the cathode equilibrium potential exerted by an oxidizing agent. An oxidizing agent is something which absorbs electrons by definition, but many of the important oxidizing agents in corrosion are also part of the way in which they absorb electrons is as part of a process in which they also absorb hydrogen ions. So this includes the two important oxidizing agents found almost everywhere in aqueous solution, that is hydrogen ions and dissolved oxygen molecules. So in both of those cases, the Nernst equation for the cathode equilibrium potential tells us because there are hydrogen ions on the left-hand side of those processes, the equilibrium potential exerted by those oxidizing agents is higher when there is a high hydrogen ion concentration. So that should make sense. A low pH or a high hydrogen ion concentration in an acid means that there's a lot of positive hydrogen ions hanging around in solution, and it should be no surprise that these environments are able to be more strongly oxidizing, because to be oxidizing simply means to be able to absorb electrons, and those protons are able to do that. So low pH, intrinsically, other things being equal, means that some of these oxidizing agents are slightly more oxidizing when there is low pH. Okay, now that we've got this idea from equation 2.58, we have everything we need in order to construct a diagram which predicts whether corrosion happens for any metal of interest in any corrosive environment, or at least any aqueous corrosive environment. That sounds ambitious, but actually we've reached the point where we can see all we really need to know about a corrosive situation is the pH and the mixed surface potential which it exerts on the metal. Both of those are easier to measure in principle for a real piece of metal in the real world, but even more important than being easy to measure is that pH and mixed surface potential taken together tell us everything we need to know about the corrosive chemistry of an aqueous environment. That's because the mixed surface potential tells us if the metal will lose electrons, and the pH tells us whether there will be some proton transfer. That's everything we need, because in corrosion we really just need to answer two questions for does corrosion happen. First question, does the solid metal dissolve into ions? That would take place by pure electron transfer or redox chemistry. That's controlled by mixed surface potential. Second question, does the metal oxide or hydroxide or whatever dissolve into solution? So that would be by proton transfer or acid-base chemistry. Taken together, if we can answer both of those questions, suppose we find out that both the metal and its oxide do tend to dissolve, then we learn that the stable phase is the dissolved ions, in which case we predict the metal is going to dissolve. It will corrode actively, meaning continuously, regardless of whether it has some surface oxide. On the other hand, if for those two questions we found the metal dissolves but the oxide does not, then maybe the metal might be passive against corrosion. With this kind of idea, we can now go and construct a pH-potential diagram which predicts what corrosion problems take place in any situation. And to construct the pH-potential diagram, we will use the example chemistry for copper metal corrosion on this table on page 21, and we will construct the diagram on page 22. Okay, so this table of example corrosion chemistry for copper, I've slightly simplified. Zinc dissolution, I said when we looked at zinc dissolution in acid that it was simple because there was only two species to consider, the zinc metal and the dissolved zinc ions. I've slightly simplified the copper corrosion chemistry so that we have something nearly as simple in this table. We're just considering the reactions of copper metal, copper 2+ ions, so I'm ignoring other possible copper ions in solution, and I'm considering the copper 2 oxide, or CuO. And so what we want to do is predict which of those things will be the stable phase, and to do that we look at the possible reactions between them. We have rows A and B of the table, which describe the two possible oxidizing agents we might need to worry about, the protons in some aqueous solution. The concentration of those will depend on the pH, and row B, the dissolved oxygen as an oxidizing agent. Then row C looks at the copper oxidation to copper 2+ ions, and we can simply describe that using an equilibrium. So we can say it's equilibrium potential. Well, if the copper 2+ ions we're considering are at standard concentration of 1 molar, then the equilibrium potential for that process is just equal to the standard electrode potential. So that's plus 0.337 volts SHE. Then if we look at row D, here's another process of copper metal being oxidized, but this time it's a oxidation of copper metal to the copper oxide. So for that reaction, we have an equilibrium potential which does depend on pH, because as well as an electron transfer, there's some proton transfer happening in this. And so we're looking at, does the copper form a oxide, which if it does, we will say is going to be a passive oxide, because let's say that it's going to be impermeable to water and it will stop further aqueous corrosion. And then on row E, we have the question, if this copper oxide does form somehow, or if we start off with some of it, does that dissolve into copper 2+ ions? So in that case, there's no electron transfer, because we have copper 2+ ions and the copper 2 oxide both have the copper atom in the +2 oxidation state, so no electron transfer, no redox. So copper 2 oxide dissolution to ions is a pure acid-base reaction. And for that reaction, we do not need to use the electrochemistry that we've looked at so far in this chapter. We just need to remember the concepts of equilibrium chemistry for an acid-base reaction. So in this case, we would need to go and look up that there is some sort of dissociation constant capital K, or reaction constant capital K, for the possible equilibrium reaction between on the one hand, dissolved copper 2+ ions and water, and on the other side of the equation, solid copper 2 oxide and 2 protons. So that is an acid-base equilibrium reaction. The equilibrium constant capital K is equal to the species raised to the power of the number involved in the reaction, with the products on the right-hand side and the reagents on the left-hand side. And in electrochemistry, we said that solid phases like copper 2 oxide and approximately pure water both have essentially unit activity, so we can simplify the reaction constant capital K to the activity of protons squared divided by the activity of copper 2+ ions. And we know that we can get the value of the equilibrium constant because we can find out the Gibbs energy change of the reaction. And use that to get the equilibrium constant. And if we do that, we can work out, we can rearrange, putting in the value of K, we can get an expression for the activity of copper 2+ ions, which will be in equilibrium with the solid copper oxide given the pH. And we get an equation which says the log of the log base 10 of copper 2+ ion concentration is 7.9 minus 2 times the pH. So that means we have a critical pH of 3.95, where if we have a lower pH than that, then the dissolved copper 2+ ion concentration in equilibrium with the solid copper 2 oxide will be bigger than 1 mole per decimeter cubed. In that case, we say below more acid than pH 3.95, the copper 2 oxide will dissolve into a solution with 1 molar copper 2+ ions, and for pHs above 3.95, so neutral or slightly alkaline pH values, the copper 2 oxide solid will be stable. Oh, excuse my cough. Now, we can take that information and draw a pH potential diagram on the next page. So the pH potential diagram starts off as an empty piece of graph paper like this, pH on the x-axis and redox potential E in volts SHE on the y-axis. On this pH potential diagram, we can draw in some environments which we might measure. So I'm imagining that I have my piece of copper and I've put it either into neutral water or into a particular nitric acid solution. And in the neutral water I've circled in blue that you can imagine I measure the pH is 7 and the mixed surface potential on the copper I measure as 0 volts SHE. In the nitric acid I could imagine I've measured the pH is 1 and the mixed surface potential on the copper is plus 0.7 volts SHE. So those are both quite possible environments. The two dashed lines on the diagram are guidelines for the two important oxidizing agents in water, or the two most important. The dashed black line at the bottom is the hydrogen line. So hydrogen ions in solution are somewhat oxidizing to things like metals, and any aqueous solution has some hydrogen ions, and once you find out the pH, you can work out the redox potential of this dashed black line, and the environment will be at least as oxidizing as this proton reaction. Because even if there's no other oxidizing agents, in aqueous solution there will be some protons, so the environment will always be at least as oxidizing as the dashed black line. And for some reactive metals, like zinc, say, that might be enough to potentially cause the metal to corrode, either into dissolved zinc ions or into some sort of zinc solid hydroxide, maybe. That's only relevant in alkali solution, the zinc hydroxide there. Now the upper dashed blue line is the oxygen reaction. So you see the neutral water, I said I've circled in blue. I've said this environment might give me a measurement on the copper which is a slightly more positive mixed surface potential than would be explained by the hydrogen ions alone. That's because maybe the solution also contains some dissolved oxygen, and the oxygen equilibrium potential, assuming 1 molar dissolved oxygen, which is unnaturally high, would be the dashed blue line. So in water, the environments you expect to find environments which will have a measured oxidizing potential somewhere between those two lines. It will definitely be at least as oxidizing as the protons, which are always present, and it could be as oxidizing as anything up to the dashed blue line, corresponding to a lot of dissolved oxygen. Incidentally, anything outside those two lines it's outside the stability window for water. So outside those two lines implies that you've added some sort of very strong oxidizing chemical or very strong reducing agent which will actually react with the water. So in the long term, your environments which you measure, like the neutral water and nitric acid I've labelled on, you expect them to have some conditions in between the two guidelines on the pH potential diagram. Okay, so the question is, once we measure this environment, what does it do to my metal? So for the copper, let's consider first of all row C from the table on page 21. So this is the standard electrode potential for copper metal turning to copper 2+ ions at plus 0.337 volts SHE. If the environment, like the nitric acid, is more positive in its in the mixed potential caused on the copper than this equilibrium line, then the copper 2+ ions are more stable than the copper metal. Conversely, anywhere below that gold line, the copper metal is more stable than the copper 2+ ions. So that's done part of our work of mapping out what is the stable corrosion product. The other part of the work is done by putting in this green line, which is the copper 2 oxide dissolution line. So this was the acid-base reaction, and we said that at any pH more acid or lower pH than 3.95, the copper 2+ ions were more stable than the copper 2 oxide. And to the right of this line, the copper 2 oxide was more stable than the copper 2+ ions. And by more stable, we're talking about we're considering a system, this is the equilibrium line for 1 molar copper 2+ ions. So more acid than pH 3.95. If I have currently 1 molar copper 2+ ions in solution, I expect there to be dissolution, so more copper 2 oxide will dissolve. Okay, so taken together, this means in the top left of the diagram I have a region where copper 2+ dissolved ions are the most stable phase. They're more stable than the metal, and they're more stable than the solid oxide. So this region I label as active corrosion, because whatever I start off with, whatever my metal starts off like, it's going to be continuously dissolving into solution, and the copper 2+ ions are not protective, so we'll have continuous dissolution or active corrosion. In the other regions, we know that we are not going to have active corrosion, but what do we have? Well, we need to add in the third equation from page 21. So row D was the equilibrium between copper metal and the solid copper 2 oxide. So that has the dashed black line for the equilibrium. So we know that if the so this was a reaction that has an equilibrium potential, and if the surface potential which we measure on the object is more positive than this dashed black line, then the solid copper oxide is more stable than the copper metal, in which case we expect the formation of copper oxide. But then we said this is going to be, I'm going to label this on as the top right region of my pH potential diagram. This is going to be called passive, because I'm going to say that the copper 2 solid oxide is impermeable to water. So this will be this will give us passive corrosion, because once the oxide forms, further reaction stops, because you then have in contact with the possible oxidizing agents in solution, you have this solid copper 2 oxide, which is quite stable. And then by elimination, we can complete this diagram. So if we are both below the gold line and below the thick dashed black line, then the copper metal phase is the most stable of all phases, in which case we say copper is immune from corrosion and it will remain in its nice metallic state forever. So that's how we construct a pH potential diagram. In this simplified pH potential diagram, which we have made on page 22, there are a couple of things just to flag up which are not completely as detailed as reality, partly because we've only considered pH from 0 to 10. If we considered pH 12 or more alkaline, there would be a region of stability for another kind of dissolved copper ion. It would be the cupric ion CuO2 double minus. So the copper 2 oxide would not be stable in strong alkali. It would dissolve into a different kind of ion. We've also ignored a small region of copper 1 oxide stability in between parts of the copper metal and the copper 2 oxide stability, but that doesn't change in principle the fact that when we find there's a solid oxide, which is the most stable phase, we say that the metal is passive, provided we think that the oxide is going to be impermeable to water. The biggest simplification we've made, though, is that we've ignored chloride. So we've only considered on the pH potential diagram the chemistry of redox and acid-base, and for the most part that is all we need to know to study the corrosiveness of an environment. But sometimes we do need to consider, in seawater corrosion in particular, we need to consider chloride. So just to show this has been done, when some research was being done into can radioactive waste be loaded into copper barrels and sunk to the bottom of the sea, can this be done safely? A more complicated pH potential diagram needed to be researched, where all of the possible copper chloride complex ions needed to be considered, in addition to the copper phases without chloride that we considered in this diagram. And so this slide shows one of the more complex diagrams which need to be considered in that case, and we find that actually even in seawater around pH 8 and in the typical redox potentials around 0 volts SHE, which we might find, we would nonetheless expect active corrosion, because as we said earlier in this chapter, the copper chloride ion is so much more stable than the copper 2+ ion. We still would expect dissolution to form the complex. Okay, so dropping nuclear waste in copper barrels to the bottom of the ocean, therefore, would not be safe, not necessarily, or certainly not for the very long term. Not if you wanted to be on the side of caution. That's what was decided for this diagram. Anyway, normally you won't need to deal with diagrams this complex. The diagrams you should see for this course, we'll just look at the zinc diagram and the iron diagram, which are two of the more important ones. So on page 23, something to note for this is that the pH potential diagrams for asking if corrosion happens are normally constructed with respect to 1 micromolar dissolved ion concentration. So that's actually the typical kind of ion concentrations you might find in groundwater or something like that. So normally, if you want to draw the region on this diagram where active corrosion happens, you want to say, is there a net driving force for the metal to dissolve into this very dilute metal ion concentration? So that partly overlaps with why in this course I said we're going to be using the approximation that ion activity is the same as dissolved ion concentration. That's because we're normally considering corrosion into very dilute solutions, where that is a good approximation. So for the zinc diagram, for example, the effect of that is that it looks a bit like the copper diagram. We have the region of zinc immunity in very reducing potentials, but we see that even the proton line, even deoxygenated solution, is sufficiently oxidizing to dissolve zinc metal into zinc 2+ ions, provided the solution is acidic. If we have mildly alkaline solutions, we have the zinc hydroxide forming a passive surface layer. So this is important in corrosion protection in practice. And if we have very alkaline, then, as would have been the case if we looked at the full diagram for copper, we have this other dissolved zinc ion, which is stable, meaning that in strong alkali we also expect active corrosion of zinc. So the effect of the 1 micromolar construction is that the active corrosion regions are simply bigger. So the equilibrium line between the metal being stable and the zinc 2+ being stable moves down, and the line of critical pH between the zinc 2+ being stable and the zinc hydroxide being stable moves to the right. In both cases, just expanding the region a bit where the zinc ion is the stable phase and active corrosion happens. So you can label those up as active, immune, and passive, and you can understand why that is. On the iron diagram, we should look at this because this is important for steel, obviously the most important metal for you to understand. Unfortunately, iron is a bit more complicated than any of the other systems we've looked at so far. That's because iron is one of the transition metals which has higher solid oxides. And also because it has a lot of different things it can do in solution. You can have Fe2+ or 3+ ions and a few other ones, and the ions in solution can actually go on and do some acid-base conversions as well. But not worrying too much about that. For iron, we see that we have in principle a region of immunity from corrosion, but that's only in redox potentials less positive than are exerted by protons on their own. So we always expect the iron metal to be unstable. It will either be turning into say Fe2+ ions. In neutral water, we do expect that to happen, or Fe3+ ions, which will happen in acid if there's some strong oxidizing action. So in nitric acid, for example, we might get Fe3+. Something more complicated, which we'll come back to in corrosion protection, is that very oxidizing environments with a high redox potential but neutral-ish pH can produce a passive, solid, higher oxide of iron, like the Fe3O4. And in some cases, this means that we can make iron passive against corrosion by deliberately exerting a strong oxidizing potential on it. So iron barrels, for example, could be used at neutralish pHs to store certain strong oxidizing agents because they would simply form a passive solid oxide on the iron. Okay. So those are some of the most important pH potential diagrams. On page 24, there are some final comments on the uses and limitations of pH potential diagrams. We have exhaustively just talked about the purpose of pH potential diagrams, so you can read that. The limitations are quite important, though. So one thing is we can look up whether for example, zinc might be corroding actively to the dissolved zinc 2+ ions on these diagrams, but that does not predict the kinetics. The diagrams would let us measure what is in some situation the driving force for corrosion. For example, if we know that the mixed surface potential is 0.3 volts more positive than the equilibrium line for the metal dissolution into whatever ion concentration there is, then that's a driving force of 0.3 volts for the active corrosion. But driving force is just one factor which goes into kinetic equations to predict how fast corrosion happens. In fact, zinc is often quite a good corrosion protection coating because despite the fact that there's very often a driving force for the zinc to dissolve, the other kinetic factors for zinc dissolution mean that it's a pretty slow process, so that my nice zinc coating on some bridge will take a very long time to dissolve, for example. And it's actually, despite being corroding actively, you can calculate it so slow, it's often a good choice for some situation. In any case, we'll come back to, it's going to anodically protect whatever other metals you have there as well as dissolving slowly itself. So a second limitation of the pH potential diagram is that they typically neglect chloride or other complexing ions. You would need to construct a new diagram, or a diagram with a third axis if you wanted to show multiple possible chloride concentrations. If you just wanted to do one chloride concentration, you could generate the more complex diagram which considers all of the possible chloride complex ions as possible stable phases which might allow active corrosion to happen. But this would quickly make the pH potential diagrams more complex, especially if you were allowing more than one complexing ion to be present at the same time. But the simple ones without chloride will frequently be sufficient to tell us that we have what corrosion we're going to have in groundwater or in many systems in chemical engineering which won't involve chloride. In seawater we would need the full diagrams which do involve chloride. A third limitation of the pH potential diagram is that they are typically constructed with equilibrium lines showing equilibrium between the solid phases and a particular solution concentrations. More complex diagrams are drawn with a multiple array of parallel equilibrium lines, each showing equilibrium with different concentrations of ions in solution. Those tend to be quite close together, so it's mostly a small correction, but you need to be aware that the lines are drawn typically for equilibrium with 1 micromolar dissolved ion concentration if we want to predict corrosion, because a micromolar dissolved metal concentration is a common one to find in groundwater or in real corrosion situations. So we say if the metal will dissolve into a 1 micromolar solution of its own ions, then we predict that it will be corroding actively. So the final limitation is that these diagrams might predict, if they predict a dissolved zinc 2+ ion is stable, then we know that there's going to be active corrosion. If they say the metal, the native metal phase is stable, then we know the system is immune from corrosion. But if they say that, say, zinc hydroxide is stable, this implies that's a solid. Perhaps this is going to be passive against corrosion, but as well as just knowing the solid hydroxide is stable, in order to confirm passivity, we also need to know something about the physical properties of the oxide. We need to know, is this oxide or hydroxide impermeable to water? So we just need that as an additional check in order to conclude that our metal is passive. Okay. In the next chapter, we'll look though at what happens if we found out that our metal is going to be dissolving actively. Then we'll be looking up how do we take our information from this chapter, the fact that there is some driving force for active corrosion. How do we construct an equation of which that's one of the inputs, which tells us how fast corrosion will happen. So that's going to be an important part of this course because, as I said, when you have your zinc coatings, often you just need to make sure you design your zinc coating thick enough to allow active corrosion to happen for the service lifetime. And we will look at equations to make sure we're able to make sensible estimates of what thickness is needed for such metals. We'll look at that next time, so we'll see that in the future. Good.